Hello, this is our presentation on investigating the effects of can height on axial crushing force, presented by Judson Levi, Ryan Lee, and Ryan Lamb. Can crushing is a process of decreasing the height of an aluminum can with an axial force. The motivation behind this project is that can crushing is performed for the purpose of recycling, as it saves space, making it much easier to transport and handle soda cans. And for our project, we looked at 3 different cans: a Poppy, Monster, and Liquid Death can. They all have the same wall thickness and diameter and are all made of the same material. The only difference is their heights.
The control variables for this experiment included the diameter, thickness, and material of the cans. The independent variable that we varied was the can height. The dependent variable that we tested for is the force needed to crush the cans. The equipment used were 3 4.8-inch cans, 3 6.18-inch cans, and 3 7.41-inch cans. A can holder was 3D printed and made sure the cans would crush in the axial direction instead of falling over to the side. A can crush helper was also 3D printed to create a stable platform to place the weights. For the procedure, we started with the 4.8-inch can and placed it into the can holder with the helper placed on top of it. Plates in 10-pound increments were then placed on top of the helper until an initial crack was heard, at which point the weight increments were switched to 2.5 pounds. When the stack of plates got too tall, a larger plate of the same weight was used to replace them. These steps were repeated for the other cans. The CAD model is shown on the right, which shows the can holder and helper. There was extra space near the bottom of the holder, so the material from the crushed cans had somewhere to go. This mitigated support that the can holder might have given the cans. The hypothesis was that the force to crush the cans would follow the Euler buckling theory with the equation shown. Since the cans are made of the same material, have the same end conditions, and have the same moment of inertia, the Euler buckling equation can be simplified to 1 over L squared. Therefore, the final hypothesis is that as the height of the can increased, the maximum axial load required to crush the can would decrease.
This slide shows our data in both a table form and in a graph. As you can see by the graph, our data follows a very clear inverse linear relationship with an r-squared value of 0.93. It follows this linear relationship at a rate of about 20 pounds per inch. While our hypothesis may have been correct, the reasoning for it was not, as the cans do not follow Euler's buckling theorem. Euler's buckling theorem is intended to be used for long solid cylinders, not short hollow shells, and it should follow a parabolic curve with length rather than a linear. Our project did have some limitations, mainly being that cans are imperfect and they do have microscopic dimples and dents, and the fact that our holder was touching the sides of the can. Despite these limitations, our project did have real-world impact, as companies making cans now know that short cans are stronger than tall cans.